Hello, please welcome to Photochemistry episode 2. So in this episode, we're going to look at the following. First of all, we're going to review the previous discussion, and then we're going to look at the absorption of light radiations by atoms and molecules. And then we're going to see what happens after absorption of light radiations. We shall also look at the Chmielewski diagram, and then the Franck-Condon principle. We shall see what's the effect of excited state. Last time, we defined photochemistry as a branch of chemistry which deals with the study of chemical reactions taking place due to exposure of a system to light radiations whose wavelength lie in the UV visible region, which is 200 nanometers to 800 nanometers. We also covered the differences between photochemistry and thermochemical reactions. We covered the laws of photochemistry, and then we saw how radiations are absorbed. In today's discussion, we're going to see the absorption of light radiations by atoms and molecules. We know that when atoms and molecules absorb light radiations, they cause transitions among the electronic levels, and these are the transitions we are talking about. When an atom or a molecule absorbs a light radiation, these atoms, they're going to be excited to a higher energy level from a lower energy level to a higher energy level. And these transitions are called electronic transitions. We can call them electronic transitions, or we can call them the vibronic transitions. Okay, and light absorbing compounds, for example, retinol. Retinol is the one that we normally use to see in our eyes. We have the different food colorings. We have the azo dyes, pH indicator, which is used to detect the acidity or alkalinity of a given solution depending on the color being given off, and many other compounds. Okay, so such compounds contain chromophores or chromophoric compounds which are responsible for the absorption of light. So the total energy of a molecule is composed of the electronic energy. Okay, is composed of electronic energy and the vibrational energy plus the rotational energy. Okay, so this is the total energy here. From here up to there, that's the total energy. We're saying that it's composed of the electronic energy, the one we are seeing here, followed by the vibrational energy. Actually, this one is the, okay, you can say rotational energy, followed by that rotational energy, and then the vibrational energy. Okay, so that's how we can get the total energy. We just need to add the electronic energy plus the vibrational energy. We say that these ones here, these larger gaps here, they are representing the vibrational energy levels. Okay, and in between the vibration energy levels, we have the we have rotational energy levels. So the ones here in between these ones here, they are called rotational energy levels. So that's how we can get the total energy. We simply get this, the electronic energy plus the vibrational energy, and then plus this rotational energy. That one will give us the total energy of a molecule. So as we all know that absorption of UV visible radiations cause transitions among the quantized electronic level. They call the vibronic transitions. We saw the vibronic transitions. We can call them vibronic transitions, or we can call them electronic transitions. And remember that electronic excitation is accompanied by vibrational energy and rotational energy. That one we've just covered it, and this is what we mean that the electronic excitation is accompanied by the rotational energy plus the vibrational energy. We say the vibrational energy, these are the larger gaps here we are seeing here, and then for rotational energy, these are the ones that we are seeing here, rotational energy levels, the small gaps in between the vibrational energy. So it means that excitation of a molecule after absorbing light radiation can be represented using these lines. To represent the excited molecule after absorbing light radiation, we can represent it by that arrow. For example, as we're seeing here, the arrow is moving from down up to this excited level. So this one here, it means that the molecule is being excited from a low energy level to a higher energy level. So we can represent the excitation by using those arrows. Here S, this one here, it means ground state, and in ground state we said we have the vibrational energy levels and also rotation energy level. So they're moving from here up to a higher excited state. S1 means excited state. So, and also we know that in the molecule, the bonding or non-bonding orbitals are generally filled up. So it means the transition occur from the highest occupied molecular orbitals to the lowest unoccupied molecular orbital. So like here, we can have a transition of electrons from sigma to sigma star. Sigma to sigma star, this kind of transition is present in single bonds. We can take an example of methane. In methane we have transition which is sigma to sigma star transition, and actually in methane we can have absorption of light around 125 nanometers. And also we have transition from pi to pi star. This one is common in ethene. Electrons will be excited from pi to pi star transition. Okay. And then from non-bonding to pi star transition, where we have electrons which are not bonded, the lone pairs of electrons. We can have an example of carbonyl groups, carbonyl compounds. These ones we know that they have the lone pairs of electrons. So these electrons, they'll be moving from non-bonding to anti-bonding orbitals. Don't forget that the electronic transition originates from a singlet state. This one here is representing a singlet state. And we know that after a singlet state, in a singlet state, after excitation, we can have a singlet excited state whereby electrons are going to be parallel to each other. While in triplet excited state, here the electrons are going to be anti-parallel. So those are the two possibilities we can have after the excitation. So as we also know that in a ground state, the molecular orbitals are occupied by two electrons, as we're seeing here, the ground state. Also, according to Pauli's principle, the spin of these electrons are antiparallel. And also, the total spin of the molecule in the ground state is 0. Why is it 0? Because the electron has plus a half, the spin of plus a half, and the other one is having a spin of negative a half. So when you add the two, you're going to get spin which is equivalent to 0. And this energy is called singlet state and is labeled as S0. So singlet state here, this one here, we can represent it as S0. Okay, and this one here we've seen that the excited electronic state can be singlet or triplet. Okay, so and we're also saying that the electrons in the excited molecule may be parallel or anti-parallel. So we say that parallel means singlet excited state, while anti-parallel means a triplet excited state. So now let's look at the characteristics of singlet and triplet states. So the lifetime of the singlet excited state is of the order 10 to power negative 9 to 10 to power negative 6. Whereas for the triplet state, it's about 10 to power negative 5 to 10 to power negative 3. So this one, as we are seeing here, that the energy of triplet excited state is lower than that of excited state. Okay, so as this one here, the energy of singlet, you see this energy is very, very, very small. I mean the time here is very small. The lifetime here is very small compared to this. So since here the lifetime is very small, it means that singlet state is less stable than triplet. Okay, so and if it is less stable, it means that a singlet state is at a higher energy level. Okay, while triplet state here means that it's at a lower energy level because this one it's a bit stable compared to this. So let's look at this one here. You see this one is a singlet. You see this is singlet 3, but look at triplet 3. So this one, look at the energy. Singlet, it's at a higher energy level. So it means that the singlet state is usually more reactive. In other words, it's less stable compared to triplet. So that's why we're saying that singlet state is usually more reactive. Let's look at the electronic transitions. We're saying that electronic transitions are governed by spin conservation rule. Okay? And the spin conservation rule, how does it state? It states that for both radiative and radiationless transitions, the principle that transitions between terms of the same multiplicity are spin allowed, while transitions between terms of different multiplicity are spin forbidden. So we can extract this statement here. The transition between the states of different multiplicity are spin forbidden. In other words, different multiplicity were meaning from moving from singlet to triplet, or from triplet to singlet. Okay, so or vice versa. That one is spin forbidden. A typical excitation from singlet to singlet is that spin allowed. Okay, singlet to singlet is spin allowed, but singlet to triplet transitions or vice versa, those ones are spin forbidden. Okay, so that's what we can extract from the spin conservation rule. Okay, so as we're seeing here, from singlet to singlet, these ones here, okay, this one is spin allowed, while singlet to triplet or vice versa, this one here is spin forbidden. Let's look at the electronic excitation or activation. The electronic excitation or activation is governed by Frank-Condon principle. So the Frank-Condon principle states that when a transition occurs from one electronic state to another, it takes place so rapidly that the nuclear or vibrating molecule can be assumed to be fixed during the transition. It means that the transition is very, very, very fast. Okay, and actually it's about 10 to the power negative 15 seconds, which is very, very fast. So in this situation, the molecule does not get an opportunity to execute vibration. Okay, so that's to say, when the electrons are excited, the internuclear distance does not change. And also, we have to know that the electronic excitation can be represented in terms of vertical arrows, okay, in energy diagram. So these ones here, the electronic transitions, we're saying that can be represented in terms of vertical arrows, and these are the arrows we're talking about. Okay, now let's look at what's the fate of excited state. 1. Remember that relaxing back to the ground state, you're going to use different processes. You have to remember that the absorbed energy is given off. The absorbed energy is given off as heat to the surrounding. And this one here, we can call it the non-radiation relaxation. So if the energy is given off as heat to the surrounding is called the non-radiation relaxation. And also the absorbed energy is emitted. If the absorbed energy is emitted as radiation, this one is, we can call it the radiative relaxation. And a radiative relaxation of excited state is called luminescence or photoluminescence. So, and this process of electronic excitation and relaxation can be represented in terms of Chomsky diagram. And this is the diagram we are talking about. So this diagram is representing electronic excitation and relaxation. Actually, we're going to explain this one here part by part. Now let's look at the excitation part. So in excited part, we're saying that the molecule in singlet ground state gets excited to any of the possible singlet state. So it can be excited to either S12 or S2, as we're seeing here. A molecule after absorbing late radiations, it can be excited from the ground state to excited states, to other excited states, for example S1 or S2, okay, as we are seeing here. What's after excitation? Okay, after excitation we're going to have two processes. One, we're going to have the radiative process accompanied by radiation emission, and also we can have another one which is non-radiative process. This one is not accompanied by radiative emission. Now let's first look at the radiative process. In radiative process, we have the vibration relaxation. So for vibration relaxation, the excited molecule in the higher vibration levels of an excited state undergo collision with other molecules. The vibration energy is lost to other molecules rapidly and fall to the ground and fall to the lowest level of the excited state. Actually here we're going to represent, as we're saying here, after a molecule absorbs light radiation, see, it's going to be at this excited state. After a short period of time, it's going to relax back, and in the process the energy is going to be given off to the surrounding. So these arrows here, they are indicating the vibration relaxation. Okay, now we can have the internal conversion. This one involves radiationless transitions between vibronic states of the same total energy and the same multiplicity. So, and also we can also have the intersystem crossing, the intermolecular spin forbidden radiationless transition between isoenergetic states of different multiplicity moving to different multiplicity. In other words, from singlet to triplet or triplet to singlet. Okay, so now this is what we are meaning, that it can either an electron can either move from singlet to triplet or from triplet to singlet. Okay, so now don't forget that the process of intersystem crossing is a process in which a spin of excited electron is reversed either plus a half to negative a half or vice versa, and change in multiplicity of a molecule. So if the spin is reversed, definitely the multiplicity of a molecule is going to be changed. So it can be changed to singlet to triplet or from triplet to singlet. That's after reversing the spin of a molecule. Okay? And actually, this intersystem crossing is most common in molecules that contain heavy atoms like iodine, bromine, and many others. And actually, the presence of paramagnetic species such as molecular oxygen in a solution also enhances the intersystem crossing. So the paramagnetic species in the solution can enhance the intersystem crossing also. Okay, so now let's look at the radiative process. Let's start with fluorescence. We can define fluorescence as a spontaneous emission of radiation from an excited molecular entity with the formation of a molecular entity of the same spin multiplicity. Okay, so as we're saying that same spin multiplicity, we're meaning that the electron will move from the singlet from S1 maybe to S0 to S0, and when it lands to S0, the energy is going to be given off. So here the radiation, sorry, it's the radiation is going to be given off, and this radiation is indicated as HV. We know that H, we covered in previous discussion that H is the Planck's constant. So this one here is represented as HV. HV means radiation, that's the kind of radiation being given off. Okay, so this is what we are saying, that when we're saying different, I mean same multiplicity. Why? Because an electron is moving, is relaxing from S to, from S1 to S0, and here the radiation is going to be given off as HV. Okay, so this is the kind of radiation which is being given off, and that one is called fluorescence. Okay, so now let's look at the phosphorescence. This one is a photon emission. As we know that fluorescence involves a spin forbidden radiation transition between states of different multiplicity, usually from the lowest vibration energy to the lowest excited triplet state. Okay, so in other words, here we can have, this is the type of transition we are talking about. So it's going to be after the intersystem crossing, the electron can move from triplets down to the singlet, and in this process a radiation is going to be emitted, and also an electron can move back, it can move from a triplet to singlet, and emission can also be given off. But this kind of emission is going to be called delayed fluorescence. Okay, it's going to be called delayed fluorescence. Okay, please. Thank you so much for watching. Thank you so much for your time. Let's meet in another episode, please.